Okay, look around the room right now. Seriously, just take a second. What do you see? A coffee cup? A laptop? Maybe a window?
I see where you're going with this. You're doing the matrix thing, aren't you?
I am totally doing the matrix thing. Because once you get the topic we're covering today, you stop seeing just stuff. You see, it's not random atoms bouncing around. Instead, you start seeing the world as this massive, invisible filing system.
Right. To a software engineer, reality isn't chaos. It's a collection of blueprints and entities. It's a way of organizing the universe.
Today, we are cracking the code literally on object-oriented programming, OOP. And before you panic and think we're going to spend the next 20 minutes reading semicolon placement in Java, just relax.
Oh, please, no. That is the quickest way to empty a room. Our mission here is really to demystify the logic behind the code. We're looking at chapter 10 of the material, but we're going to translate it from, textbook into actual human speech.
So whether you're a manager trying to figure out why your developers keep talking about inheritance and polymorphism, or you're just curious how we model reality inside a silicon chip, this is for you. We're going to break down how these abstract ideas turn into functional software.
Yeah, and we've got a great set of notes today, slides that cover everything from the basic definitions to real-world analogies like libraries, gardens, car rentals, plus some code snippets in Java, C++, TY, and Python that kind of illustrate the universal truths across all of the languages.
So let's start at the very beginning. The genesis of everything in OOP, the split between the blueprint and the reality. Or, in the jargon, the class and the object. Unpack that for me.
Well, to understand this, you kind of have to imagine a world without it. So imagine you're running a library, but you have no system. You just have a pile of books.
Chaos.
Total chaos. Every time a new book comes in, you have to write down every single detail about it from scratch on a blank sheet of paper. This has pages, it has ink, it has a cover.
That sounds exhausting and so prone to error, you might forget to write down the author on one of them.
Precisely. That's the Wild West of coding. Object-oriented programming solves this by creating a class. Think of the class as a rubber stamp or a blueprint.
Okay.
In our library example, the book class is that template. It says, listen, if you are going to be a book in this system, you must have a title, an author, a genre, and an availability status.
So the class isn't the physical book itself. You can't actually read the class.
No, the class is just the concept, the rule book. The object is what happens when you use that stamp, when you take the blueprint and actually build something. So a physical copy of To Kill a Mockingbird sitting on shelf A4. That is an object. It follows the rules of the book class, but it has its own specific data.
I like that distinction. So the class says all books have a title. The object says my title is 1984.
And this is where it gets interesting, because objects aren't just, lifeless data containers. They aren't just a list of facts. They have behaviors.
Which the notes call methods.
Right. A book in a library isn't just sitting there. It interacts with the system. It can be borrowed, which changes its status to unavailable. It can be returned. It can be reserved. In code, those actions, borrow, return, update, those are the methods.
So to synthesize this, a class bundles the what it is, which is the data attributes, and the what it does, the methods, into one nice, neat package.
That is the core philosophy, and it works for anything. I mean, the material gives a car rental example. The class is car. Attributes are make, model, year. The object is that specific Toyota Corolla you rented for the weekend.
And the methods would be rent, return, or check mileage.
Exactly. Or the botanical garden one, which I thought was surprisingly detailed.
Oh, the tree class.
Yeah.
Yeah, the class defines species, height, age. The object is the big oak near the entrance. But the methods were cool, like photosynthesize or grow.
Grow is a perfect example of a method because it modifies the data. When the grow method runs, the height attribute actually changes. The object updates itself.
Okay, so we have the mental model. Blueprint creates object. Object has data and does stuff. Now, I want to get into the anatomy of code section because the notes bring up something that I think confuses a lot of people. Identity.
You mean this and self keywords?
Yeah. The notes show examples in Java, C++, A, and Python. In Java and C++, A, you see this .name. In Python, you see self.name. It looks like just syntax noise, but it feels like it's doing something, I don't know, philosophical.
It's basically object self-awareness.
Explain that.
Okay, so imagine I'm in a room full of people and I shout, say your name. Everyone shouts at once. It's just chaos. But if I walk up to you specifically and say your name, you know I'm talking to you.
Right.
In code, the computer needs to know. Are we talking about the variable name that exists vaguely out there in the universe? Or are we talking about my name, the name belonging to this specific object?
So this literally means me, as in the object I am currently inside of.
Yes. When a Python object says self.name Alice, it's saying set my internal name variable to Alice. It distinguishes the specific instance's data from everything else in the program.
That distinction between my data and general data, that actually leads us to the first big stumbling block in the notes. The battle between instance methods and static methods.
Oh, this trips everyone up. It really does.
The notes define instance methods as relying on a specific object, while static methods, they belong to the class itself.
Think about it this way. Let's stick with the car analogy. Driving is an instance method. You can't just drive in the abstract. You have to drive a specific car.
You need the keys to that Toyota.
Exactly. You're interacting with that specific object's engine and wheels. But what about traffic laws? Do traffic laws belong to your Toyota?
No, they apply to all cars.
They're universal. Stop at a red light is like a static method. It doesn't care if you're in a Ford, a Ferrari, or a Honda. It applies to the class of drivers generally. You don't need a specific car object to know that 2 + 2 = 4.
Ah, okay. That's why math functions in code are almost always static.
Precisely. So if I'm writing code and I need a function that just does a calculation and doesn't care about any specific user's data, I make it static.
Yeah.
You call it using the class name, math.squareroot. You don't create a new math object just to do multiplication. That would be really wasteful.
Okay, I think we've got the foundation. We know what objects are, how they identify themselves, and the difference between my stuff and universal stuff.
Yeah.
Now we get to the meat of the episode, the 4 pillars.
The 4 pillars of OOP. These are the sacred rules. If you understand these, you really understand modern software engineering.
Let's hit the first one, encapsulation.
This is often called data hiding.
And this is where I always play devil's advocate. The notes say encapsulation is about bundling data and methods and restricting access using private variables. My question is, it's my code. I wrote it. Why am I hiding data from myself? Why put a lock on a door I built?
It's a fair question. And it's not about hiding it from you, the architect. It's about hiding it from you, the tired developer at 2:00 a.m. Or the other guy on your team who didn't read the documentation.
Okay, paint me a picture.
Look at the bank account example in the notes. You have an attribute called balance. Now, if you make that variable public, that means any part of your entire software system can reach in and just change that number directly.
Balance of 1,000,000. I can see the appeal.
Sure, but what if you accidentally type balance equals 0? Or what if you accidentally set it to a negative number? If the data is public, there are no guardrails. You can break the logic of the entire system with just one typo.
So encapsulation is the bouncer.
It's the bouncer and the bank teller.
Yes.
By making balance private, you're saying you cannot touch this number directly.
So how do I update it then?
You have to go through a public method like deposit or withdraw. Yeah. And inside that method, we can put rules. We can say if the withdrawal amount is greater than the balance, then reject the transaction.
Ah, so the method acts as a gatekeeper. It checks your ID before it lets you in.
It creates a safety interface.
Yeah.
You don't mess with the wires. You just press the buttons we gave you. It keeps the data valid and secure.
That actually makes a ton of sense. It's idiot-proofing, even if the idiot is me. Let's move to pillar number 2, inheritance.
The lazy coder's best friend.
I prefer efficiency enthusiast.
Fair enough. Inheritance is simply the mechanism where a new class can take on the attributes and methods of an existing class. It's all about not reinventing the wheel.
The notes use the classic animal example here.
It's a classic for a reason. It's so clear. You create a parent class called animal. You give it the basics, a name, an age, and a method called eat, because, all animals eat.
Right.
Now, you want to make a dog. Well, a dog is an animal. So instead of typing out name, age, and eat all over again, you just say dog extends animal, and boom, the dog automatically has all that stuff.
But a dog isn't just a generic animal blob.
No, of course not. And that's the beauty of it. You can then add specific things to the dog class. You add a breed attribute. You add a bark method.
So the child class gets everything the parent has, plus its own special features.
Exactly. And this creates a whole hierarchy. You can have a cat class that also extends animal. It gets the basics, but then adds meow.
I feel like there's a trap here, though. I mean, as a senior developer, do you see people overdoing this?
Oh, absolutely. We call it inheritance hell.
Sounds pleasant.
New developers love it. They'll make a golden retriever that inherits from retriever, that inherits from dog, that inherits from canine, that inherits from mammal.
And suddenly you have to trace back like 10 files just to figure out why the dog won't eat.
Exactly. Inheritance is powerful, but you should only use it when there is a strict is-a relationship. A dog is an animal. A sports car is a car. If you find yourself forcing it, you're just creating spaghetti code.
Good warning. Okay, pillar number 3. This is the one with the sci-fi name, polymorphism.
Many forms.
The definition in the notes is enabling a single interface to represent different underlying forms. That sounds like a legal contract. Can you translate that for us?
Okay, let's move away from the animal example for a second. Think about a video game controller.
Okay, I'm holding a PlayStation controller in my mind.
You've got the X button. In the game's code, that button is just a signal, button pressed. But what happens when you press it?
Well, it depends on who I'm playing as. If I'm a soldier, I shoot. If I'm a wizard, I cast a spell. If I'm in a car, I brake.
That is polymorphism. The input is the same press button, but the behavior changes based on the object.
So in the code, the game engine doesn't need to know every little detail of the character. It just sends the action command.
Yes. Without polymorphism, you would have to write this massive, ugly list of rules. If character is soldier, then shoot. Else if character is wizard, then spell. Else is F.
The else if ladder of doom. I've written that.
It's a nightmare to maintain. With polymorphism, the game engine just says, current character dot attack. And if the object is a soldier, the soldier class knows how to shoot. If it's a wizard, the wizard class knows how to cast a fireball. The engine doesn't care how it happens, just that it happens.
That makes the system incredibly flexible. You could add a new character, a space alien or something years later, and you wouldn't have to rewrite the game engine. You just teach the alien how to attack.
Exactly. It's like a plug-and-play system. The notes mentioned the shape drawing app example, which is the same logic. You have a list of random shapes. You just loop through and tell each one, draw. The circle draws a curve. The rectangle draws lines. The main program is simple. All the complexity is hidden inside the objects.
Which leads us perfectly to the final pillar, abstraction.
The user interface of life.
The notes define this as hiding the complex implementation details and showing only the essentials.
We live our entire lives relying on abstraction. Think about the car again. When you sit in the driver's seat, what do you see?
Steering wheel, pedals, dashboard.
Do you see the fuel injectors? Do you see the catalytic converter? Do you see the logic board controlling the anti-lock brakes?
No, and frankly, I really don't want to.
That's abstraction. The car manufacturers have created an interface for you. You press the pedal, which is the interface, and the car goes, the implementation. You don't need to know how the engine works to drive to the grocery store.
And if they change the engine, swapped it from gas to electric, the interface stays the same. I still just press the pedal.
Bingo. In code, abstraction allows us to change the messy details in the background without breaking the code that other people are using.
The notes talk about abstract classes here. This is a bit of a weird concept, a class that isn't fully there.
Think of an abstract class as a promise. Let's go back to our shape example. I can create an abstract class called shape. Inside it, I create an abstract method called calculate area.
But how do you calculate the area of a generic shape? You don't know if it's a square or a circle or what.
You can't. That's why the method is abstract.
Yeah.
It has no body. It's just empty.
So what's the point of an empty method?
It forces the children to do the work. It's a rule that says, look, if you want to be a shape, you must figure out your own area. The circle class must write the code for pi times r squared. The rectangle class must write length times width.
So it guarantees consistency. Every shape is guaranteed to have an area calculation, even if they all do the math differently.
Right. It allows the architect to design the structure of the system, the what, without worrying about the implementation, the how, until later.
So if we look back at this whole journey, we started with a chaotic world. We organized it into blueprints or classes and reality objects.
Then we protected the data with encapsulation. We stopped repeating ourselves with inheritance.
Made the system flexible with polymorphism. And finally, we simplified the whole thing with abstraction.
It's not just code, is it? It's a philosophy of management. It's how you handle complexity without going insane.
It really is. It's how we build these massive systems like banking networks or operating systems that are way too big for one human brain to hold all at once. We break it down into these little self-contained objects.
Before we wrap up, I have to mention one thing I found in the notes. It was buried at the very end, under the question slide.
Oh, I think I know what you're talking about.
The note regarding the assignment due date. It said, we should be nearly done with the semester at this point. Don't be a jerk and assign something else.
I saw that. That is the voice of a professor who has seen the light. Yeah. Or maybe a teaching assistant who is just done.
Just do your assignments in Canvas and bring yourself to class to learn. That's solid life advice, honestly.
It is. Focus on the learning, not the busy work.
So here is my final thought for you, listening right now. We talked about abstraction hiding the messy details behind a clean interface. Think about your day today. You tap a glass screen on your phone, and food appears at your door. You turn a key, and a machine takes you to work.
You are surrounded by objects.
You are. We're all just users pressing buttons on these massive, complex interfaces we don't understand. Does knowing how the code works, how the sausage is made, does that make you appreciate the world more? Or does it just make you worry about the encapsulation failing?
I think it makes you appreciate that it works at all. It's a miracle of engineering.
It certainly is. Well, thanks for helping us decode the blueprint today.
Anytime. It was fun to peek under the hood.
And thank you for listening to this deep dive. Keep looking for the classes and objects in your daily life. We'll see you next time.